Section: Introduction. In this section, we excel at predicting the next word. However, we also face challenges with hallucinations, where our responses may seem correct but are actually incorrect or nonsensical. Detecting these hallucinations is crucial for ensuring reliable performance. To tackle this, we introduce a method to either provide a trustworthy response or abstain from answering altogether. We measure the success of our method by looking at the rate of abstention and the risk of hallucinations in the responses. Previous approaches have focused on using probabilities to detect hallucinations, but this can be unreliable as the length of the response sequence can impact the likelihood. Instead, we explore using uncertainty and agreement between multiple responses as indicators of potential hallucinations. We address the challenges of determining response similarity and identifying hallucinations by developing well-crafted prompts and leveraging statistical techniques. Our method does not require modifying the model itself and is based on prompting. We evaluate our approach on various question-answering tasks and find that abstaining with self-evaluation outperforms traditional methods. To automatically evaluate experiments, we introduce a calibration method based on conformal prediction, ensuring accurate match predictions even with small calibration datasets. We define the problem we are addressing and outline our approach. We consider input prompts and output responses, with a match function determining if responses are equivalent. Our goal is to develop a selective classification scheme that can abstain from making predictions when necessary. We introduce score-based abstention functions and define a loss function to evaluate the performance of our selective classifier. To find the optimal abstention threshold, we use a calibration dataset to design our abstention policy. This dataset consists of query response pairs and helps us determine a threshold that minimizes abstentions while controlling the risk of incorrect answers. By optimizing this threshold, we aim to strike a balance between accuracy and abstention rate. Section Summary. In this section, we introduce the challenge of hallucinations in language model, LLM, responses, where the model confidently generates incorrect or nonsensical answers that are hard to detect. To address this, we propose a principled abstention policy that either provides a reliable response or abstains from answering altogether to mitigate hallucinations. By leveraging conformal prediction techniques and self-evaluation prompts tailored to each query, we aim to minimize the risk of hallucinations while optimizing the abstention rate in LLM responses. Section: Choice of the score function and the classifier. In this section, we discuss our selection of the score function G and the classifier F. We start by adding K samples to each question-answer pair, X_I, Y_I, which are generated from the language model, LLM, based on a query X. This results in a calibration data point of the form X_I, Y_I, Y_1_I, L dots, Y_K_I. It's important to note that in many cases of using LLMs, we already have multiple responses for a given query, so adding K responses does not increase computational load. We can set K to be the number of responses the LLM typically generates. We consider two score functions. The first one, called match count, is based on a contextual similarity function S and a positive scalar parameter beta. By default, we recommend using LLM prompting to measure text similarity, but other functions can also be used. For a query X and generated responses Y_1, L dots, Y_K, the score of response Y_I is the count of other responses similar to Y_I based on the parameter beta. The default response F, X, is the one with the highest score, and the score G, X, is the score of F, X. If the score is below a certain threshold lambda, the policy abstains. Otherwise, it returns the response F, X. Using LLM prompting for similarity has been effective in practice. Calculating the score function requires K² additional inferences, which can be computationally intensive. One cost-effective alternative is to compute the similarity of each response with all others in a single prompt, which is faster. Another alternative, called expected match count, involves asking the LLM in one query about the number of matches among other responses for each response y(i). This method provides a more detailed optimization range but requires access to the LLM's log probabilities. A simpler approach is to choose F as the greedy output of the LLM and calculate the score based on the number of similar responses in the other samples. This reduces computation costs by a factor of k and is known as the greedy version of the methods. Moving on to the choice of the match function, we can derive match functions from similarity scores where two responses match if their similarity score exceeds a certain threshold. For short answers like in the Trivia QA dataset, we use the recall score to evaluate methods. However, for longer responses as in the temporal sequences dataset, we use LLM prompting to determine if the generated answer matches the label. This is done by asking the LLM to measure the similarity of the texts given a question on a scale of 1 to 10. If the score surpasses a set threshold, the text is considered a match. The calibration of the match function is detailed alongside the experiment descriptions. Section Summary. In this section, we discuss the choice of the score function g and the classifier f for the LLM. We augment each question-answer pair with k samples generated from the LLM, and consider two score functions, match count and expected match count, which offer different computational trade-offs. The match function is derived from similarity scores, with options like the F1 score or recall score, depending on the length and nature of the responses being evaluated. Section: Conformal Abstention. In this section, we aim to create a post-processing method that ensures our final policy is close to optimal for the problem at hand, using the calibration dataset. We observe that the loss function decreases as the parameter lambda increases. If the policy assigns a high score to a sample for a smaller lambda, it will also do so for a larger lambda, with both cases resulting in zero loss. The function f is independent of lambda, leading to smaller or equal loss for larger lambda values. By leveraging the CRC framework, we can tune lambda based on the calibration data and test points interchangeably, given the non-increasing nature of the loss function with respect to lambda. To enhance decision-making reliability, we need confidence guarantees that hold with high probability over the samples, rather than just in expectation over the calibration data. We can convert an expectation-based guarantee to a high-probability one using methods like Markov's inequality. However, we can further strengthen this guarantee through an amplification technique, albeit with data splitting. This amplified inequality provides a high-probability assurance for the CRC procedure, though slightly less tight than the high-probability guarantees discussed later for RCPS. The CRC procedure ensures the constraint inequality is met but does not offer insights into how the abstention rate of our solution deviates from the optimal rate. Under certain assumptions, we can bound the difference between the optimal abstention rate and the one obtained from the CRC procedure. Section Summary. In this section, we introduce the concept of conformal abstention, where we aim to construct a post-processing method using calibration data to ensure that the resulting policy is close to optimal for a given problem. The loss function decreases as the parameter lambda increases, and by leveraging the CRC framework, we can effectively tune lambda based on the calibration data and maintain high probability guarantees for reliable decision-making. Additionally, while the CRC procedure provides an expectation-based guarantee, we can enhance it through high-probability amplification methods to improve confidence levels over samples. Section: RCPS. In this section, we were motivated by the need for reliable guarantees on the calibration data, so we introduced a new set of methods called RCPS. When our loss is bounded by 1, we can achieve a high probability outcome for wide-hat lambda_n using conformal risk control. This result depends on C, delta, alpha, n, equals U, delta, n, V, alpha, n, where the probability is based on the calibration set D_n. By rewriting hat lambda_n, we see that using conformal risk control is the same as using the distribution-free RCPS method for a Hofting UCB on the empirical risk at level alpha plus C, delta, alpha, n. This is supported by Theorem 2. The RCPS method is more versatile than CRC because it can handle non-monotonic loss functions. We aim to select wide hat lambda to ensure that the loss L, x, y, wide hat lambda, is less than or equal to hat R underscore UB, wide hat lambda, with high probability over the calibration set D underscore n. We explore various upper confidence bounds for RCPS, including the empirical Bernstein inequality and the Bernoulli relative entropy inequality. Additionally, we discuss the Wadby-Smith-Ramdas (WSR) inequality for non-binary losses, which is more suitable for such cases due to its better adaptation to variance. When it comes to calibrating the match function, we face challenges in determining if two responses to a query are the same. We focus on score-based match functions, where a similarity score S is used to define a thresholded match function M. The goal is to select a threshold beta that aligns the match function M with the ground truth based on the similarity score S. We can calibrate beta using a calibration set and ensure that the match function reflects the ground truth as accurately as possible. By properly calibrating beta, we can use the match function to estimate the true error rate. This calibration process involves considering the number of incorrect LLM responses and ensuring that the reported errors based on the match function provide an upper bound on the true error rate. By setting beta according to conformal prediction rules, we can guarantee the behavior of the match function on new data. This approach allows us to control the expected number of errors made by the LLM and ensure reliable performance evaluation. Section Summary. In this section, we introduce a family of methods called RCPS, which provide high probability guarantees over calibration data, even for non-monotonic loss functions. We consider various upper confidence bounds for RCPS, including the empirical Bernstein inequality and the Wadby-Smith-Ramdas inequality for non-binary losses. Additionally, we discuss the calibration of the match function to accurately compare responses, highlighting the importance of selecting the threshold beta to minimize errors based on the match function. Section: Related work. In this section, we delve into the research related to uncertainty quantification of machine learning methods. We focus on prior studies closely linked to our work. One area we explore is selective classification, where the goal is to design an abstention policy for a given classifier, training set, confidence parameter, and desired risk bound to ensure the risk stays within the specified bound with high probability. Some past work has used a binary search method, but due to the non-monotonic nature of the loss function, this approach may not always meet the risk condition. Selective question answering in scenarios where the test point may be out of domain is also examined. This ties into the RCPS approach discussed earlier. Additionally, we look at abstention in large language models, LLMs, focusing on methods that utilize a pre-trained model rather than fine-tuning LLMs. Some studies have explored different score functions for designing an abstention mechanism, with varying levels of success. Another area of interest is detecting hallucinations by generating multiple responses and comparing them to a reference response. While some methods show promise, they may have limitations in practical applications. Furthermore, uncertainty quantification of LLMs and reasoning with LLMs are also discussed, each proposing unique approaches to address model uncertainty and decision-making processes. Token probabilities are commonly used to quantify uncertainty, but their effectiveness may decrease with longer text generations. Additionally, LLM self-prompting is explored as a method to measure model uncertainty, although it may not be as effective as sampling-based techniques in certain cases. Section Summary. In this section, we focus on related work in uncertainty quantification of machine learning methods, particularly in the context of selective classification. We discuss prior papers closely related to our work, including approaches that use pre-trained models for abstention in LLMs and methods for quantifying uncertainty using token probabilities and LLM self-prompting. These studies explore various techniques such as generating multiple responses, measuring similarity, and reasoning paths, highlighting the importance of designing effective abstention policies and quantifying model uncertainty in machine learning applications. Section: Applications of conformal prediction in quantifying uncertainty in LLMs. In this section, we have explored various applications of conformal prediction in quantifying uncertainty in language models, LLMs. We have seen how conformal prediction can be used to create confidence sets of text outputs that contain acceptable answers with high probability. Additionally, we have discussed using conformal prediction to calibrate parameters in nucleus sampling and to quantify uncertainty in LLM-based planners for multiple-choice style tasks. Furthermore, we have delved into other methods for quantifying uncertainty in deep learning and LLMs, such as ensemble methods. These methods involve training multiple models on perturbed versions of the data to estimate confidence intervals. While ensemble methods can be seen as approximations to Bayesian methods, they often require validation on holdout data for hyperparameter selection. Our experiments aimed to test three hypotheses related to conformal abstention, loss measurement for detecting hallucinations, and the effectiveness of different scoring methods for long answers. We conducted our experiments on two question-answering datasets, temporal sequences and trivia QA, with a focus on evaluating the performance of various calibration methods and score functions. For calibration methods, we considered CRC and three variants of the RCPS procedure, along with a baseline method. We also explored different scoring methods, including match count, expected match count, and log probabilities. The choice of similarity functions and thresholds varied depending on the dataset characteristics, with a focus on minimizing errors in response evaluation. Overall, our experiments shed light on the effectiveness of conformal prediction and different calibration methods and scoring functions in quantifying uncertainty and improving the performance of LLM-based systems in question-answering tasks. Section Summary. In this section, we explore the applications of conformal prediction in quantifying uncertainty in language models, LLMs. We investigate using conformal prediction to design an abstention mechanism and construct confidence sets of text outputs with acceptable answers. Additionally, we experiment with different calibration methods and score functions to verify hypotheses related to mitigating hallucinations and improving performance on question-answering datasets like temporal sequences and trivia QA. Section: Results on the temporal sequences dataset. In this section, we conducted experiments on the temporal sequences dataset and the trivia QA dataset. We tested 4,000 question-answer pairs on the temporal sequences dataset with two different risk tolerance levels, alpha equal to 0.05 and alpha equal to 0.1. We used a delta value of 0.05 for the failure probability in confidence intervals. The results of these experiments are shown in the figures and tables mentioned in the paper. We observed a trade-off between abstention rates and test errors. A higher abstention rate led to lower test errors, but some methods showed better trade-offs than others. For example, the log probability scoring method performed worse compared to the match count, MC, and expected match count, EMC, methods, regardless of using CRC or RCPS for conformal prediction. The empirical Bernstein calibration method performed significantly worse than the others due to its specialization for Bernoulli random variables. On the trivia QA dataset, we tested 1,000 question-answer pairs with risk tolerance levels of alpha equal to 0.1 and alpha equal to 0.2. Similar to the temporal sequences dataset, we used a delta value of 0.05 for the failure probability. The results are presented in the figures and tables provided in the paper. Comparing the experiments on both datasets, we found that the match count-based calibrated abstention methods outperformed the log probability-based method. The match count methods performed well for both short and long answers, while the log probability scoring method showed significant weaknesses for questions with long answers.